Hello, my name is Denis Gopen. I am a scientist at GrammaTech. In this talk, I will describe the work on system configuration modeling we did under DARPA Configuration Security Program. This was joint effort with Vlad, Rebecca, Thomas and Wutze. Modern computer systems, ranging from simple home networks to complex DoD infrastructures, are built by cobbling together general-purpose commercial and open-source components, such as routers, workstations, general-purpose operating systems, and popular software packages, like web servers and database management systems. These components are built to support many diverse usage scenarios, and must be properly configured to work together. So what's the big deal? Complex network-composed systems are being stood up every day. We rely on them routinely in our day-to-day lives. It turns out, however, that configuration can be quite tricky. Often, configuration mishaps result in security holes. These configuration-based security holes are typically easier to exploit than conventional software vulnerabilities. Even when not exploitable directly, misconfiguration may extend the attack surface of the system. According to the last year's Verizon's Data Breach Investigation Report, 8% of all security breaches are caused by misconfiguration, but for some key areas, these percentages are significantly higher. So what makes system configuration hard? First, configuration is often used to impose global system-wide constraints. For instance, for the remote clients to successfully communicate with a central server, the communication endpoints must be configured accordingly. The port numbers must match, the encryption-decryption parameters must agree, and so on. This complicates making configuration decisions and adjustments locally. The local changes often have a profound system-wide effect. Second, to manage complexity, systems are typically built by stacking together multiple abstraction layers. Each abstraction layer is individually configured, and the layer configurations are combined in non-trivial ways so that the overall effect of the configuration is often hard for a human to understand. The diagram on the right illustrates some of the layers that participate in determining file access permissions on a typical web server. At the lowest level, the file access is governed by POSIX file permissions. On top of that, there may be a layer of rule-based security, such as SE Linux or AppArmor. The OS will check the effective user ID of the web server process to determine what files it can access. Finally, a web server implementation may provide its own custom facilities for managing user permissions. All of these layers are combined to determine whether a web server may serve a particular file over an HTTP connection. To illustrate the challenges that configuration poses, let us consider the following notional scenario. In this scenario, two seemingly benign configuration changes, when combined, result in weakening the overall system security. Our example system is a small company network which has two human users, a manager Mary and a developer Dave. Both Mary and Dave have access to their respective PCs, as well as to a shared development server. Mary, as a manager, also has access to a secure company server. She uses public key authentication to access that server. The company security policy states that only managers are permitted to have access to the secure server, and so far, under the current configuration, this policy is met. Now, suppose Mary finds herself spending a lot of time working on the development server. She wants to simplify access to the secure server, and so she copies over her private key from her PC so she can connect to the secure server directly. Dave also spends a lot of time working on the development server. He frequently needs to have new packages and tools installed, or existing ones updated, and so he requests extra privileges from the IT department so he can do it himself. In response, the system administrator naively configures sudo to give Dave full root access to the development server. When taken separately, these two changes are marginally justifiable. Together, however, they combine to cause a security breach. Dave can now use his root level permissions on the development server to steal Mary's private key and use it to access the secure server, in effect violating the company's security policy. There are a couple of general observations I would like to make here. First, it is hard to predict the global effect of local configuration changes. Here, for instance, local configuration changes that were made to the development server enabled unauthorized access to a completely different part of the system. Second, potential fixes for the configuration issues like this, for instance putting in place a more fine-grained pseudo policy, only complicate things further and makes it even harder for humans to perceive the system-wide effect that such configuration changes may impose. In this work, we explored applying formal reasoning to the problem of system configuration. Specifically, we worked on designing formalisms and methodology for constructing a concise, self-contained, logical description of a system that links its behavior to the values of its configuration parameters, and that enables us to effectively query relevant system properties. Our initial focus was on access control. The high-level property we were targeting was what system resources are accessible to a particular human user. A human user being an actual person that has a certain degree of physical access to the system, as well as certain knowledge of system credentials. Returning to our example, we can establish whether the company's security policy is satisfied by checking the following property. Can someone who has physical access to Dave's PC and knows passwords to Dave's accounts log into the secure server? If this property holds, the policy is violated. An interesting thing to observe about this property is that it combines concrete configuration options, such as file permissions, SSH configuration, and user account setup, with notional aspects, such as physical access and human knowledge. The ability to formally reason about such high-level access control properties has a number of useful practical applications. The initial motivation for this work was configuration synthesis. The formal modeling framework allows us to set up configuration synthesis as an optimization problem. Essentially, synthesis must pick configuration values that maximize the security of the system subject to its functionality constraints. A more simple and direct application is configuration analysis. The modeling framework allows us to check whether a system configuration agrees with the desired security policies and to debug problems with system functionality, or even perform a what-if analysis. Investigate how potential configuration changes affect system behavior prior to deploying them to the real system. Other applications include red teaming and penetration testing. A model can help determine whether an outsider with minimal knowledge can gain an access to sensitive system data, and if so, derive a sequence of steps for how that can be accomplished. Internal threat management. We can use a model to detect access privileges that are not essential to system functionality and ensure that privileges are properly revoked when no longer needed. And the forensics analysis. Say we know that a particular user account has been hijacked or a set of system credentials has been stolen. A model can be used to estimate the breach perimeter, sort out which data could have been leaked, and which data can still be trusted. Let me give you a brief high-level overview of how our modeling approach is structured. At its foundation is a modeling formalism we developed. It is a general declarative modeling language that provides an ability to define and compose reusable modules. It also supports high-level data types and provides static typing. For the sake of truth in advertising, I have to admit that in its current state our language is geared towards machine consumption, and as such is closer to bytecode or an intermediate representation than to a regular programming language. We are actively working on designing a developer-friendly front-end for it. We used our modeling language to build a library of reusable system building blocks. The library defines low-level primitives such as network interfaces, firewall rules, users and groups, files, and directories. The low-level primitives are in turn used to define higher-level concepts such as network connectivity, local and remote host access, and file access. Given a target system, the model is constructed by instantiating and stitching together library primitives in accordance with the system composition. This process is easy to automate, as long as the library contains the necessary primitives. The model separately captures the assignment of values to the configuration parameters. These could be collected from the target system or supplied manually. Ultimately, the model defines a deductive database, a set of facts that capture low-level system data, and a set of rules for deriving more global, higher-level system information. To check system properties, we compile the database into Prolog program and use off-the-shelf Prolog interpreter to answer the queries. We found this approach to be adequate. However, we do not advocate using it in practice. We believe that much more effective querying mechanism may be designed and employed. One option is to see how far we can get by using datalog engines, such as Souffle, in place of Prolog. Datalog is decidable and supports mechanisms for effective query evaluation, such as the magic transform. Another alternative is to apply existing SAT and SMT solvers to evaluate deductive database queries. This may involve a degree of approximation to deal with recursive predicate definitions. Perhaps ideas from bounded model checking and abstraction refinement-based verification can be applied here. Let us now take a deeper dive into how the modeling operates. We will use our running example to illustrate. The model sets up two actors, Mary and Dave. They're shown on the left in the diagram. The actors are used to track the knowledge that the corresponding human system users possess, as well as the devices that they can physically access. The predicate actor access checks whether an actor, Dave in this case, can log into a host, the secure server, as a specific user. Note that user in this example is a free variable. When the predicate is evaluated, the solver, a Prolog interpreter in our case, will attempt to tie it to some system entity in a way that satisfies the predicate. In the subsequent slides, I use capitalization and color to separate variables from the direct references to system entities. The first step in evaluating actor access predicate is to establish what devices the actor can physically access. In this case, this is derived trivially from the actor setup. Next step is checking network connectivity. Is there a network route from Dave's PC to the secure server that can be used to establish an SSH connection? The net access predicate captures the underlying network configuration, such as routing and firewall access control lists. The predicate itself has a complex definition. We will not expand it here for brevity though. We will just assume that the predicate holds for the sake of the demonstration. Finally, the remote login predicate checks whether Dave is able to log into the secure server. Let us expand its definition. The predicate first checks whether the server runs a remote login service, SSH in this case. Then it checks whether SSH enables password-based authentication. Finally, it checks whether Dave knows a suitable password that will let him access some user account on the server. In this case, Dave does not know any relevant passwords, and thus the predicate fails. The model then tries alternative definition for the remote login predicate. This definition checks whether Dave can log in using public key-based authentication. I will not go through this definition in detail. Ultimately, the question boils down to whether Dave has a read access to a file that contains a suitable private key. This check is performed by the actor file read predicate at the bottom of the screen. For brevity, let us skip a portion of derivation and go straight to the most important part, the access to Mary's private key on the development server. To check that, the actor file read predicate establishes that Dave is able to access the development server, that he is able to impersonate the root there due to weak sudo configuration, and that as root he is able to access Mary's private files. So, in the end, our original query is satisfied, showing that Dave is able to log into Mary's account on the secure server, violating the security policy. To summarize, our configuration modeling framework systematically explores modeled resource access mechanisms. It supports parametric queries, not just yes or no questions, and it provides an ability to track the steps that need to be taken in order to access the resource. Let me cover our practical experience with the modeling framework. Under DARPA's configuration security program, we used our framework to model Navy's training system for capture the flag cyber exercises. The subset of the system we modeled included about 20 hosts sitting on roughly half a dozen subnets. For each host we modeled users and groups, a selection of files, and a handful of services. The resulting model had around 2,000 parameters. Some of those, like firewall rule lists, were of composite types, lists of records rather than scalars. Overall, the model had around 4,000 facts and 200 rules. We used the model to check a number of functional and security requirements for the system. The box on the right provides an idea of the kind of requirements we've considered. The functional requirements specified the level of access that users with a certain role must have. For instance, web administrators required read and write access to web server configuration files. Web developers had to be able to inspect web server logs and edit the web content. The security requirements aimed to enforce the principle of the least privilege. Essentially, they tried to systematically take away access privileges wherever possible. In all, the requirements were reduced to about 10,000 individual queries. Even with our unoptimized Prolog-based solving approach, it took under 2 minutes to evaluate all of those. Next, I'd like to take a step back and talk a bit about the design principles we tried to adhere to in this work. The challenge with practical configuration modeling is the sheer number of existing software packages. Making custom analysis extensions for every additional package we wanted to support was clearly intractable. To address this challenge, we took inspiration from the retargetable frameworks for binary analysis and reverse engineering, such as NSA's Ghidra. These frameworks lower software binaries from various platforms to uniform microcode, essentially allowing the backend analysis to be implemented in a platform-agnostic way. Following that route, we designed a general modeling language that allowed us to capture the semantics of various platforms and services. We used the language to start compiling an extensible library of reusable primitives. When building those primitives, we strove as much as we could to avoid specializing their logical encoding towards a specific target analysis or a specific solving technique. Rather, we tried to capture as much precision as possible in the model and leave approximation and optimization to the backend solvers. We believe that this makes our library usable across a wider spectrum of potential applications. Finally, when fully constructed, our system models essentially correspond to deductive databases, a paradigm that is well known and well understood. This allows application of the existing effective querying mechanisms and also simplifies development of novel querying approaches. Let me highlight several directions of further research that we are contemplating. First, constructing models for software packages manually is not tractable at scale. Some degree of automation is desired. We believe that configuration modeling provides an interesting new target for program analysis, both for applying existing mechanisms and for developing novel techniques. Another interesting research direction is the validation of configuration models. Modeling is only useful as long as it accurately reflects the real life. Our modeling primitives were defined manually. There is a good chance that they contain bugs or omit important system behaviors. Effective mechanisms that can cross-check the models against the real life would help detect and manage such imprecisions. They will also boost the confidence in the modeling framework and in the analysis tools that are based on it. Finally, there is a question of scope. So far, we have only focused on modeling access control properties. We believe that our approach can be further extended to cover additional properties that are important to system security. This may include tracking the data encryption, the use of SSL certificates for establishing trust between communicating parties, and possibly even some social and psychological aspects of system use. To conclude, we are building a configuration modeling framework that uniformly captures various system configuration aspects, uses a well-understood logical encoding, and enables mechanical construction of models for complex systems by combining predefined reusable building blocks. I'd like to reiterate that this work was sponsored by DARPA and the Configuration Security Program. I would also like to thank other performers on that program for their insights and encouragement. Thank you.